How's it going, everyone? In our previous look at the trapezoid rule, we saw what would happen or how the trapezoid rule is really just adding together the areas of a bunch of trapezoids that are defined by the curve that we're trying to estimate area under. Today we're going to try to speed up that process by looking at some special circumstances which allows you to create not similar in the sense of geometry similar, but similar trapezoids with respect to their height. I'll show you what I'm looking at over here on the next screen. As we start off, we're going to be looking at the Raptor Squad, which I think is hilarious. So here with the Raptor Squad, you can read more about these. Deinonychus versus the raptor as in Jurassic Park, but we'll get back to it later. So here's the idea. We're going to be computing a trapezoidal area very abstractly. Okay, so we know we have a function over here, and just to give us a little bit of background, if we had some kind of a function, and if this was the x-axis down here, x-axis, and over here we would have f of, let's say that's x1, and this is f of x2, that would make this point right here, x1, comma 0, and this point over here, x2, comma 0. And the area of this trapezoid here, well, this we would call this base 1. And we would call this over here base 2. And this distance from here to here, that would be the height, which would happen to be a difference in the x-coordinates. So the height is x2 minus x1. So if you want to implement the trapezoidal area here, the area would be 1/2 of base 1 plus base 2 multiplied by the height. And I can't believe I ran out of room there. Let's write it over here. So the area would be 1/2 of f of x1 plus f of x2. Since f1, f of x1, that would be the height of base 1. And f of x2 would be the height over here, this vertical distance. And then the height over here, or the distance between these two, that would be really a delta x, x2 minus x1. So what we're going to do is we're going to kind of take a look at this table here, and we're going to fill it out. And if we have x0 to x1, delta x is delta x, of course. 1/2 base 1 times base 2 plus base 2. That's 1/2 of f of x0 plus f of x1. And so the area of that trapezoid would be 1/2 delta x, f of x0 plus f of x1, which is kind of the same thing that we have over here. So let's go ahead and fill out the rest of these. For this second interval, delta x is delta x, of course. 1/2 base 1 plus base 2, that's 1/2 of f of x1 plus f of x2, and that gives us an area of 1/2 delta x, f of x1 plus f of x2. Now this third column here, that's even less fleshed out for you. However, if we just follow the pattern here, this is going to be 1/2 of f of x2 plus f of x3, and then this will just down over here, we're just going to multiply. So we get the area of that third trapezoid is 1/2 delta x, f of x2 plus f of x3. Now, if we want to find the area under the curve, and we can kind of visualize that, I'm going to scroll up a little bit here, as something like this, where we're adding all three of those trapezoids together. Now when we add those trapezoids together, well, we're just going to put all of these area formulas into this equation. So as you can see, we've got this 1/2 delta x f of x naught plus f of x1 plus a 1/2 delta x f of x1 plus f of x2 plus a 1/2 delta x f of x2 plus f of x3. Well, this brings us to our special conditions. The special condition is, what if all these delta x's were the same for each term here? Well, if each of these delta x's were the same, that means that we can factor them out. We could also factor out the 1/2, but that should be kind of given here. So if we factor out that delta x and the 1/2, we're just going to put all of these terms together in the same sum. F of x naught, f of x1, another f of x1, another f of x2, another f of x2, and then an f of x3. So that's what we're going to write here, where I is going to be that an estimate of that integral. We're just going to add all of those that we just previously stated. It's important to realize that we had one f of x naught, but we had 2 of f of x1, and we had 2 of x2, f of x2, and we only had a single f of x3. Now I'm sure you can see from here that we can group here, so we would get 2 f of x1s and 2 of f of x2s, and that would look something like this, where we've got 1/2 of delta x plus, or times a quantity, f of x naught plus 2 f of x1 plus 2 f of x2 plus a single f of x3. And if you did this for a number of trapezoids, let's say we had more than 3 trapezoids, let's say we had 10, well, you would find out that the first y value is always going to happen once. Everything after that is going to occur twice, and then the very last y value is only going to happen once. So that means that through induction, we've built this trapezoidal formula where as long as all the delta x's are the same, we can just do the 1/2 delta x multiplied by the sum of the first f of x naught plus double all of everything else except for the very last one, f of xn. So some wisdom here. The key is to double each interior f of xk, but not f of x naught and f of xn. So don't double the first one, don't double the last one, double everything else. The other thing to realize is that you're never going to be required to use a trapezoidal formula. You can do trapezoidal rule for estimating area without ever touching the trapezoidal formula. However, it does make things faster under the right conditions, and it's also really easy if you're going to be going into computer science. It's going to be really easy to calculate something like this. So that would be a main attraction of why you would want a trapezoidal formula. We already know that the trapezoidal formula is only going to work if delta x is the same for each interval. If we're looking forward to the AP test, on the free response section, you're not going to get delta x the same for every interval. I don't think I've ever seen that on an AP test where the trapezoidal formula was actually what was being tested. And lastly, concave up functions are going to produce overestimating trapezoids, and concave down functions are going to produce under approximating trapezoids. Let's take a look at that. So here we have that same trapezoid that we were looking at earlier in the problem, and let's imagine what a concave up function is going to look like. So we're going to draw a concave up function that connects the two corners here. And well, yeah, that's kind of what it would look like if I was going to use a trapezoidal formula on a concave up function. And you will notice that the area of the trapezoid would be greater than the area underneath the curve. So the area underneath the curve in that same sliver, yeah, it's definitely smaller than the area of the trapezoid. So because the area of the curve is less, the concave function on a concave function, the trapezoidal approximation will be an over approximation. Well, what about a concave down function? Okay, let's draw a concave down function and let's see what would that look like. Okay, here's a pretty decent looking concave down function. And if I was to look at the area of this sliver under the concave down function, I'll notice that the concave down function has more area than the trapezoid. So since the trapezoid has less area than underneath the curve, a concave down function will be an under approximating for that trapezoid. So that's just a quick look at that. Naturally, or maybe not naturally, I don't know. If you have a function that's partly concave up and partly concave down, then you really can't say whether or not your trapezoidal approximation is going to be an over approximation or an under approximation. It needs to have the same concavity for you to say that conclusively. Problem. Use the information in the table of the trapezoidal formula to estimate this integral. Well, maybe we should start off by seeing if we can use the trapezoidal formula. So let's check out all the delta x's. This delta x is 2. This delta x here is 2. This delta x here is 2. And I think you're going to see all of our delta x's are going to be 2. So we can use the trapezoidal formula to calculate the integral, or to estimate the integral. First thing you're going to want to do is write out that trapezoidal formula. So the integral from 0 to 10 of f of x dx, that's going to be approximately equal to, again, approximating because we're using a numerical method here. Trapezoidal formula is a numerical method. That's 1/2 delta x. And we'll go ahead and, let's see, f of x naught. Let's see, we have x naught, x1, x2, x3, x4, and x5. So we're going to go to x5. Plus 2 times f of x1, plus 2 times f of x2, plus 2 times f of x3. This guy won't erase. Plus 2 times f of x4, plus 2 times, no, this is the last one, f of x5. Okay, that's how the trapezoidal formula works. Okay, approximately equal to 1/2. Delta x is 2. We measured that up here. Delta x is equal to 2. And it's the same delta x for every trapezoid. Okay, f of x0, that is 10. 2 times 28, 2 times 38, 2 times 44, 2 times 47, and then 48. Okay. As you can see from here, it's just calculator work. So let me grab a calculator and do this. And I get a 372. No units are presented in the problem, so I'm not going to worry about units here for this. Okay, trapezoidal approximation. I hope you can see that that greatly speeds things up. No more calculating each trapezoid individually. Just put it all together in the formula, as long as all the delta x's are the same. Okay, here's some important ideas. Naturally, the important idea here would be that trapezoidal formula. And like I've been emphasizing, it's a faster way to do the trapezoidal approximation, but it can only be used if the interval widths for each trapezoid is the same. Let's do this, check your understanding. The tail of Deinonychus is roughly half the body length of the dinosaur. The measurements of Charlie, that's one of the raptors in the Raptor Squad, found that her tail was approximately 1.6 meters in length, and Charlie's tail circumference at different distances along the base of the tail is given on the chart. So we're going to use a trapezoidal method to estimate the surface area of Charlie's tail. So I know that's a lot of context, or a fair amount of context, but the only thing you really need to know is that if I multiply circumference times a distance, that's going to give me surface area. That is the surface area formula. Circumference multiplied by distance. So we're going to use the trapezoidal formula here, and let's check. Can I use the formula first of all? Are all the delta x's 40? That's definitely 40. This is definitely 40. 120 minus 80, that's definitely 40. And then yep, definitely they're all 40. So I can just go ahead and use the trapezoidal formula. So we're going to do the integral from, where are we going? From 0 to 160. And we're going to multiply the circumference. Let's call that c of x, and dx, where c is circumference and x is the distance from base of tail. So cx dx, that would be circumference multiplied by distance, or change in distance. So that's going to be, well, cx dx would be an expression that gives me the an estimate for the surface area of one section of Charlie's tail. So that's neither here nor there, because we're going to use the trapezoidal formula. That's going to be 1/2 delta x, and that's going to be c, why did I write an f? C of 0 plus 2 times c of 40 plus 2 times c of 80 plus 2 times c of 120 plus c of 160. Notice how this first term and this last term do not get multiplied by 2. Let's substitute numbers now. 1/2 delta x is 40. C0 is 81.8 plus 2 multiplied by 24.2 plus 2 multiplied by 20.7 plus 2 multiplied by 10.4 plus, well, 0. Now it's just calculator work. My calculator says that the integral is going to be 3848 square centimeters. So Charlie's tail has an approximate surface area of 3,848 square centimeters. So that's it for our look at the trapezoidal rule and using specifically the trapezoidal formula. Hopefully that helps you out when you get this on your AP test, and I'll see you guys next time for more calculus.